Lesage gravity, or more specifically Fadio gravity. Gravity, the version of gravity that was first proposed, say, some 300 years ago, maybe even before that, that there's actually a force, a physical substance that's causing gravity. And that the universe is full of this energy stuff, and it's an external pressure that is pushing objects into each other. Not really a very difficult conception. I mean, there's only two answers, right? I mean, it's pulling or it's pushing, and then pushing is kind of so much simpler an explanation, so you just try to figure out what's pushing. And clearly what's pushing isn't a big giant hand or something, right? It's not a bunch of angels flapping their wings or any of that kind of stuff, because we'd have video of that. So it's something ultra mundane, something small like photons. They're often invisible. Can't see them. They make stuff happen, okay, without us knowing it's happening, why it's happening. So that would be a good cause to speculate about, and then it just sort of works in the sense that they constructed it into something called Mach gravity because it works as a force, and there's only a couple of problems. And Bob attempts to go through those problems. He points the problems out very well, but doesn't really explain why they're not problems very well. So I'll explain why they're not a problem. Why, if you really understand how it works really, really well, and it doesn't have any deficiencies. It completely explains gravity. So the moral of the story, the context is that 300 years ago they had an 80%er kind of theory, something just it makes a lot of sense, but there's these kind of problems. It just falls apart in the sense that it stops making sense. And but like I said, if they had that extra 20%, if they knew why it seemed broken, then it wouldn't be broken anymore. So it's like little things, it does something that's out of the ordinary. Like water's one of the few substances that expands as it gets colder, and it seems anti-intuitive, wrong. It's like, what is that molecule? Alien or something? No, but there's an explanation. And so it doesn't, you just have to wait for the explanation, and then it fits again. You say, oh, okay, it's possible for this special circumstance to exist, and you can understand why it's behaving like an alien. Now, it's not really an alien. You find it in nature, right? There's animals that seem kind of absent, out of place, and can't be explained simply, but because there's a more complex explanation, some special circumstance where they're isolated and then they, become unisolated, whatever, blah, blah, blah. So, and that's all that this conversation needs, is an understanding that there's some presumptions people make about how gravity functions, and those assumptions or presumptions are incorrect. When you understand that it's possible for it to behave in some other way, then you can understand how it can work. So I will attempt to deal with what are essentially, so the idea is that yes, Lesage gravity was discredited by the 1900s. Nobody would take it seriously because they had decided, they had already tried to fix it and they couldn't fix it, and so they threw it away for good, so to speak. They basically told people, don't look at it, don't try to fix it. We tried, we couldn't fix it, give up. And then we got bent space anyway, which is not an answer to anything. Bent space just tells you what you already know. There's an inverse square rule. Yeah, we already know that. We already know there's a proportional increase in the strength of the force as you get closer and all that stuff, and they just drew it differently and said, there, it looks like a well, so there, well, think of it like that, when it really doesn't behave like a well. It behaves like a convergence from all directions. No well-like functions. Anyway, All right, so there's three problems: heat, drag, and aberration. So let's take them in a different order. The heat problem seems kind of funny, okay, just because it's kind of obvious that the Earth is hot in the center. We kind of already know that it's molten and full of activity, and that's essentially giving you some clue that, well, what's causing all that hotness in the center of the Earth? Well, it's obviously the gravitational tension is the only reasonable explanation, and the tension is really being created by the fact that the Earth is heavy, and it's every bit of ground is pushing towards the center of the Earth and creating intense pressure in the center. So I mean, yes, heat is a consequence of gravity. Things get big enough, they're going to get hot, and that seems totally correct and intuitive, so it's not really an issue. At the time the idea was first proposed, people were trying to make the gravity instantaneous. That means the little bits had to move at really, really fast speeds, and so they would have had a lot more energy and all of that stuff, and so, that's where it kind of fell apart, was in this need for it to be instantaneous. So that gets you to the second subject, which should be aberration. So heat and aberration are sort of related because they're both connected to an idea that you make your gravity as you're interacting. That gravity is a event that takes place between two objects in some personal way. Like, it doesn't exist when the two objects aren't interacting with each other. And yes, it's the only way you can measure gravity is to put an object in the gravity. So it always has to be personally measured, but it's not personally happening. The single object has gravity. So, in brief, hopefully, somewhat brief, a little bit brief, whatever, try our best. I guess we'll click this, and we'll get my chalk back. Yeah, that looks all right. All right, so the aberration argument would be at the speed of, if gravity had a speed, like the force bits are moving at a speed, the argument is that you get kind of far away, like we are from the sun, 8 minutes one way. The idea would be is that it takes 16 minutes for this round trip, that is for your change in the shadow. Okay, let's say you're creating a shadow, and let's represent the shadow as an absence of force, as a jagged line, let's just say. So you understand that's a shadow. Okay, that's the absence of stuff, because stuff hit this, it didn't get here. That's the simple argument. This absorbed the energy, okay, and it's now moving this way. Okay, it has a velocity this way, and it's now moving this way because it's getting hit by this external force that's coming from everywhere. And it's creating a shadow on the sun. And the sun, likewise, is saying, I'm not getting hit by anything, so I'm going to move towards this, because there's a shadow on this side and there's the same force. Oh, gee, dropped my chalk. Tragedies everywhere. It's tough being me. Anyway, so the sun is also getting hit by a force, and so it will move into this low pressure, and when it moves, it's absorbing the force, right? The movement is absorption. Movement means you've taken a force that was going the speed of light, and you've hit an atom or something, and that's moving much less than, double less than, right? Triple less than c. So the force is now occupied doing something not going where it was going. So it's not here, right? It's not going to get here. It's stuck moving this thing really slow. But when this thing finally gets here, obviously all that force will be there. So the force is here. It's just, in a different form for a little while. It's really not. But anyway. So you get the idea, right? So the point would be is that it takes 8 minutes for this message to get to the sun, and then when the sun moves, it's going to move to where the Earth was, right? So all of this stuff absorbed is going to be absorbed. It's going to cast the shadow the sun's going to cast the complementary shadow where the earth was when it was casting its shadow. And then the earth's going to be in this position, though, by the time that shadow that the sun casts, the earth will have moved. And so the shadow is going to be, there ain't going to be nothing there. So it's going to cast a shadow where there ain't no planet, where there ain't anything to be disturbed by it. So that's the concept of aberration. Now, the problem with that theory is, again, this idea that all the gravity is being created by the interaction itself. And the fact is, you don't fall into the gravity you're causing. So when you fall into the earth, you know, if you're up in the air and you're falling into the earth and you're absorbing force, okay, by falling, moving, you're not, you know, the earth doesn't actually move. The earth didn't move ahead of you to create that gravity, right? So that gravity already existed. The gravity you fall into is gravity already, the earth has already made. And it was made by, you know, this hunk of the earth, you know, the dead guy, let's just say. There's a dead guy in here, right? So he's totally dead, lying inside the earth, and he's still falling. He's still being pushed by gravity. He's still absorbing momentum. And the fact is that you can measure it, because, you know, if you go down there and stick something in there, you'll see the ground tend to want to fill the hole back up because there's pressure, okay? And the pressure, it exists, the counter pressure. And so obviously, you know, if there's a pressure going this way and something isn't moving, so it's not moving, well, then you kind of know there must still be a pressure going this way. All right, so that's the truth of it. Gravity's already here, and the gravity's being caused by the earth itself, because the earth has inside of it collected a whole bunch of dead stuff, you want to call it that, or he's collected a whole bunch of junk. And by collecting that junk, the junk is all being pulled into the earth. And you can sort of understand that, well, pulled is the wrong word. It's all being pushed by the external force. You can sort of understand that this stuff, you know, when it moves a piece of crap this way in the earth, that absorbed a force. And so now there's a shadow on the junk over here, say. And so this piece of junk feels the shadow and it moves this way. And then when this one moves, that means it absorbed a force. It absorbed this arrow, you know what I'm saying? So it absorbed it. It's now stuck here. It's not going to get over here. So this piece of stuff says, oh, more stuff's hitting me from the outside than the inside. I'm going to move this way. Well, when it moves, that means it absorbed the force. That means the force ain't going to get over there. So the earth is constantly creating a shadow in all directions. All right. So in all directions, there is a shadow being caused by the fact that these competing actions are taking place. And from each side of the earth, you only see the shadow. You don't see the re-emitted energy. So although the earth is expelling, okay, as much as that's coming in, the fact is that when you're sitting here, you can't see force going this way. So you can't see any of the extra force going out this way. You only see stuff going towards you. And towards you, there's a deficit, not a extra. And so you can't see the other side of the force. You know, you can't see the opposite reaction, if you want to call it that, whatever you want to call it. All right, so how else to better illustrate this? So the point is that there's no aberration problem, because the absorption of the force is in all kinds of directions. So you could argue that any one of these arrows of a force, okay, has a component in this direction. So it has a component from here, it has a component going that way and that way. And from here it has a component going this way. And yeah, we don't need another component. And this one would have a component going up and a component going in. So the only part that matters really from the purpose of gravity, that is something sitting here, is those components. So you could block a force that would hit it this way, or you could block a force hitting it this way, and lots of different ways. And the same is going to happen in how the shadow is going to be cast. It's going to be cast in all directions, and evenly in all directions. So it doesn't matter where the Earth is, because the Earth isn't falling into the gravity it's making. It's making gravity for somebody out here, right? Somebody out here, okay, in a sense, is going to feel the shadow created by the sun when the sun moves a little bit towards the Earth. See, when the Earth is moving towards the sun is really moving towards the Earth also. It's just that it's a much smaller part of the sun that's moving towards the Earth. Just an Earth-size piece of the sun, an Earth worth of mass. So that would be a little bigger because the mass of the sun, the density of the sun is so much less than the Earth, so it would be a bigger piece of the sun. But there's an equal exchange. It's just that this part has to drag the entire sun with it. So obviously it takes a lot more movement in that mass to move the sun as fast as the Earth would move. Because the sun has to drag all the rest of the matter with it that isn't being affected by the Earth's shadow. So anyway, so the simple answer to aberration is that gravity, by the inverse square law, is in all directions. And there is no aberration, because the gravity you create can be the equal and opposite reaction. That is, you block something going this way, it can come back to you in any one of these directions, okay, as long as when you add them up, it has the same arrow length in your direction. So it could be like 10 of these, or 1 of these, or 7 of these, because they have a component in the right direction. And so so the gravity is equally dispersed, and it's not something you're creating until, like, when you get on the surface of the sun, then the Earth will just be part of the gravity the sun makes. All right, just makes the sun more massive, and it will increase how fast something accelerates into the sun, because now the sun has more mass, which means it is now blocking more force, or using more force, let's say, at any 1 minute. So the point is that inside the sun, there's stuff going this way, there's stuff going this way. And the real point is the only thing the Earth can see, okay, the Earth is sitting here saying what's happening. It sees the absorption of force. So when something's moving inside the sun in this direction, everything's swirling inside of it too, just like inside the Earth, the molten part's swirling. The swirling thing is representing the fact that force is being consumed for it to move. It can't move unless something pushes it. It doesn't have perpetual motion. It has to keep getting pushed to move. All movement requires a force to be consumed. And so from this perspective, you see this getting consumed. You see this stuff coming in that's causing motion in the sun. But the opposite reaction, from your perspective, is invisible. There's no way for you to see the effect of absorbing force going this way, right? I mean, there's no way for you to be affected by somebody doing something to something's going away from you. If something's disturbed, I throw a baseball, and something doesn't throw it back at me, how the hell do I know? I don't know anything about it, right? If it's dark. I can only know the stuff that was heading right for me, and somebody sticks up a glove and stops that ball from hitting me. I can know about that. But I can't know about the stuff going away from me that never was going to hit me. So if somebody throws a baseball and goes by my head, I don't care whether that gets blocked. I'm not going to know. I'm not going to know anything about it. So we know about this. We don't know about that. And that's the position everything is in from every single position around the sun. It's the same circumstance. This guy will see this absorption, but he's not going to see this absorption. So he's going to see the shadow created in his world by this event, but he's not going to see the shadow over here created by the opposite event. All right, I think that explains it well enough. I think. It's nice that this is actually erasing almost without water. Huh. It's a little bit fuzzy, but not terrible. All right. So we'll pause for a moment and continue. It appears that I'm recording again. Hope so. Anyway, so I have the right slide up there. Yeah. Little mini me over there. Cool. Anyway, alright, so what else did I want to add? So I wanted to connect the heat argument to the aberration argument. Just point out that obviously what's taking place inside of something gravitational is that the stuff inside is in fact, to create a shadow, it's absorbing the energy. The energy comes in, it's absorbed in the sense that it now attaches itself to an object. Okay, I would argue it makes an exchange with the object, but doesn't really matter. And the object moves, and it moves much slower than the force, so the force doesn't get where it was going. And in the case of an object, you can understand it doesn't even get where it was going inside the object itself. All the other places it could have hit, it doesn't hit, and they keep going in some direction. And so the point would be is that this is happening from all angles. And what you end up with is a bunch of stuff going this way, and a bunch of stuff going that way, and a bunch of stuff going this way, and a bunch of stuff going that way. And that's what heat is. Heat is dispersion. So when, say for example in a conductor, if you move the electricity by moving the electrons evenly, and so you don't have any less heat, because the movement of the electrons is all in the same direction. But if this little energy bit ends up going this way, and then it goes this way, and then it goes that way, and then it goes this way, and then it bounces and bounces and bounces and bounces. You can see the number one, it doesn't get from here to there. Okay, it stays in the conductor, and each one of those hits is movement in a new direction. It means something else doesn't get hit. It means it moves in another direction because it didn't get stopped. It's like a bunch of pendulums swinging, in different directions. And you're just keeping the chaos by having stuff constantly going in different directions, hitting it, where if it's coherent in its movement, not dispersed, correlated, culminated, then it won't have much of a heat profile, in the sense it won't be doing a lot more interactions. There'll be a lot fewer interactions while it's in the substance than if it disperses and goes in different directions and ends up hidden, having lots of interactions. So the more interactions, the more heat is really what it comes down to. And scattering the interactions means the energy will be in here longer, simply. The more crooked the path, the longer it's in here. The straighter the path, the less long the energy is influencing anything. Simple enough, I think. Okay. Should be good enough. Alright, so we'll pause again. Alright, looks like I'm back. Alright, so the drag subject, he doesn't have really a good slide for drag, just pointing out what the problem would be. And the simple explanation is that as something moves into a field force, a force that would be going, there would be stuff moving in all directions. Obviously, as you move forward, you're less likely to hit, if you were hitting stuff that was, in the field, the stuff going the same direction as you, there's little chance that you're going to hit that. because no matter where it is, it's going as fast as you, and there's more chance that you're going to hit the stuff going in the opposite direction. So the argument would be the faster you go, the more of this stuff you hit, the more it takes velocity away from you, because it's a real force. It's not a fake force, it's a real force. It's going to have a real impact on your ability to move through it. Now for the force itself, if it was just hitting force with force, you can sort of understand that they can just hit each other and bounce off instantaneously without losing a step. Or go right through each other, or whatever the rule might be, and it wouldn't make any difference, for force itself. Couldn't care less. No hindrance to the force itself, but the material objects clearly are given a partial momentum by their interaction with the world, and that partial slower momentum is quite vulnerable to this fact that it would start degrading as it moved into the force. It's going to encounter more force the faster it goes. So I've proposed a simple solution to the problem, which is basically just the idea of having two elements, and that the first element, okay, they're both going this way, and the first element is the one getting hit by more force, and it's essentially protecting the other element from the extra force. So if you could imagine there was a bit reflecting between these two. Okay, so it's just going back and forth like a ping pong paddle. And as it goes back and forth, it imposes forward momentum when it goes forward, making this thing go forward, right? And then it reflects and goes back and then stops the object, the mechanism that is connected to each other. So this mechanism is connected in a sense by a spring, by some mechanism that allows it to move, out of place, but that the two things share the momentum. So any momentum this gets, this one's eventually going to get it. So they're tied to each other through a force, or through a force reflection or mechanism, but at the same time they're capable, okay, of exchanging momentum. The simple way to look at it is it's a mechanical box, and you're putting energy in a direction, and the energy stays inside. So it's like the ping pong paddle example. Alright, so say if you had two ping pong paddles like that. How to simplify this drawing. So there would be a state of equilibrium. There's this bounce rate, so it goes forward in the sense that it gets momentum in the forward direction, makes the exchange, which means the momentum goes in the backward direction and the object moves forward. And then when it hits this back one, that's the stop, okay? And then it has the reflection, and now it's going to hit the forward again and start it moving again. So I showed an animation of that in the last video. So I don't know if I want to really go over that. I'm just trying to go over the part that you could sort of understand that as the forward object hits more force, right? So let's just say now that I'm going to accelerate it. Now it's going to hit more of this. That the consequence would be that this backward object, because it keeps moving every time there's this reflection, so this direction. So if I make this stop sooner, and I cause the reflection at this point, then it's going to take less time for this to get to here, which means this reflection is also going to show up sooner. So the closer I make these two objects, the more interactions I create in both directions. I mean, these are the stop direction, this is the forward direction, and there's an equal number of them. But the key point is that with each one of these there's forward momentum, and that will meet the opposing force. So as the object moves through space, it acquires equilibrium. That is, this distance will be equal to the amount of force it's encountering. And if I increase the amount of force, or I increase the speed, all I have to do is decrease the distance between them. As I decrease the distance between them, I'll increase the amount of times it gets pushed forward. And the times it gets pushed forward is equal to the amount of force hitting it. Force coming at it is the same as saying interactions. So if there's 5 force bits interacting, well, you could argue that, okay, if I increase that to 10, then all I have to do to equalize the opposing force is to increase the number of hits on this one in the forward direction to 10 in the same amount of time. And as long as that takes place, this thing will keep going. So the idea would be simply argued that as you increase the velocity of the object, what you're really just doing is changing it from that distance to this distance. And so this could be 5,000 miles an hour, and this could be 50 miles an hour, and it's just going to change the rate at which there's reflections, which changes the rate at which there are interactions in the forward direction, and that will be commensurate to the increase in the number of likelihoods of encounters with the force coming against you. So you're going to encounter more impacts, and you can easily compensate for that by just increasing the number of impacts taking place between the two objects. And as you increase those impacts, you'll increase the capacity to meet the force. So that would be the simple mechanism. I guess I should show the animation again, right? That would be the thing to do. So let me do that. So I'll be back again. Ah, jeez. You know, now it's trying to play the DVD. Stupid, stupid, stupid. Anyway. Try again. Alright, it should be the right video now. It should stay that way, hopefully. Anyway, so as you can see, if I can squeeze that circle, those two surfaces, I would create faster interactions. And faster interactions means essentially more energy in a direction. Both directions in this case, and the two directions are forward and off, forward and off, forward and off. There is no opposite direction yet, because you're just taking away velocity. You're changing the amount of velocity. You're going from moving to not moving. You have to go through not moving to get to moving in the opposite direction. So the fact that that middle thing is in there means that the object will just keep going in the direction of the initial momentum, and the smaller I make that object, the more force in a direction, in the forward direction, it'll be able to overcome. Because it will have it will just keep going forward. It'll do it just faster. It'll do it at a faster rate. It'll jiggle at a faster rate and compensate for any drag that's being imposed by the fact that it's moving faster. But that's why it's difficult to accelerate objects, is because the coefficient means that you have to always add a little extra to keep pushing it forward, because you have to compress those objects, and that compression is real energy that has to be consumed. It's real pressure you have to create. Yeah, and maintain. So, yeah, I guess that's enough, I think. So it's perfectly consistent with what we see in the real world. I guess I would argue also for the drag argument that I would argue that the elemental bits, the electrons and the protons, are in fact dragged, and that's why they don't get to us from outer space. Stars, suns blow up, all kinds of stuff happens out there, and the electrons and the protons don't get to us. The only form they get to us in is in a clump of a nuclei from, say, helium, which is an arrangement of electrons and protons, a simple arrangement that allows for this function. So by arranging electrons and protons in a specific orientation, you create one of these little devices that'll just keep moving through space forever, because there is no loss.